Welcome to the show. Today we're unpacking a critical environmental crisis in the American Southwest that connects wildfire smoke to your drinking glass: wildfire pollution in the Rio Grande. Our team, Robert, Simon, Liam, and Jaden, have been studying the causes and, crucially, the solutions. The core issue, as seen on the slide, involves three things: a wildfire event, the subsequent runoff into the Rio Grande, and the chemical component that makes it dangerous: nitrates. When extreme heat burns through forests, it rapidly turns stored nitrogen into soluble nitrate, which is then easily washed into the river system. It is an invisible pollutant with massive impact.
Now let's take a look at key stakeholders affected by wildfire debris in the Rio Grande. First, we have public health officials who are responsible for monitoring and managing the safety of our water supply, since debris contamination can pose serious health risks. Next, wildlife is directly impacted, as debris can destroy habitats and reduce water quality. The New Mexico agriculture industry also depends on the Rio Grande for irrigation, so debris buildup can hurt crop yields and equipment. New Mexican citizens rely on the river for recreation, drinking, and cultural value. The New Mexico water utilities industry faces higher treatment costs and system strain from debris. And then finally, the New Mexico Department of Energy and the state government have an interest in making sustainable water management and protecting national resources. As far as solution requirements, when designing our solution, we want to keep it within legal restrictions and make sure it's cost effective to implement and maintain. Our design also should provide long-lasting effects and improvements that are better than the current conditions. Finally, it must be unintrusive to wildlife and ensure that the ecosystem remains balanced while also addressing the problem. By meeting these requirements, our solution aims to protect both people and the environment in a sustainable way.
Alrighty, and now moving on to our solution. Let's start off with the solution design itself. First on the materials. We're going to be utilizing an ASA plastic shell due to its high UV resistance and its durability, also for the fact that it is usable in 3D printing, and that is actually the main method we're going to utilize to create the solution's exterior shell. Second, we are using a stainless steel mesh at the inlet and the outlet of the device. This is in order to stop fish from entering, allow water through, and also keep it rust resistant. And then at the bottom, you'll notice there is a biomedia and nitrate-eating bacteria, which I'll get into a little bit more later. Second, we're moving on to our features. At the bottom, you'll also notice there are spikes and there is a weighted bottom, which will anchor the device to the riverbed, stopping it from shifting back and forth or even being taken away by the current. Then we have a water inlet and a water outlet, which will control the water flow, slowing it down. The reason we need that, along with our inner chamber, which is much larger than you would expect, is to create a lower oxygen environment with slower moving water, which is critical for our bacterial culture, as they need a low oxygen environment in order to convert nitrates into nitrogen gas. How you'd use it is print out the device, add the culture into the biomedia, wait about 24 hours for it to activate, then place it into the river, and the bacteria will naturally eat nitrates, releasing oxygen and nitrogen gas, the same that you'd find in chips. Now, how did we test it? When we made our prototypes, we placed them into a fake river. Then we inserted a nitrate salt in order to artificially simulate a wildfire and the nitrates that brings. Then we added probes before and after the device as the water circulated in order to measure the nitrates. Over time, nitrate levels dropped at both probes, with more drop at probe B, which was after the device.
The data we measure is nitrates in water conditions. After a wildfire, nitrate levels were 76 parts per million. After our solution, it was 64. This is a 12 parts per million decrease. How we measure water conditions is total hardness and alkalinity. Hardness started high, and after our solution, it was decreased to only 20 parts per million, while hardness went to none. We also took carbonate, which was high pre-wildfire. After our solution, it was 20 parts per million. The pH levels also slightly dropped. What engineers do is design and optimize water system pipes. Engineers also create resilient water systems that can withstand droughts, floods, and contamination. The role of computer scientists is to develop algorithms and softwares for water monitoring. They also use data analytics to detect leaks. Construction managers oversee the building of the water system so they don't collapse and follow safety regulations and environmental standards and on time. You can learn more by sources such as ASC or IEE's water-related projects. You can also engage with open source water data platforms to practice analysis. You can connect with local water utilities or resilience initiatives to gain experience. You can also review prototype documentation or presentations such as this one.